So last time we talked about how to land a spaceship. Which is one of my most favorite topics ever. Super fun. Along those lines, by the way, I believe Friday this week, Vandy Verma from JPL, who's one of the lead rover people at JPL, who's also an RI alum, is going to be here and giving a seminar talk on sort of JPL Mars robotics, which should be super awesome. So you should check that out for sure. Did everyone get that email today? Went out? Yeah. So you should definitely check that out if you're not too busy carnivaling. Should be cool. On the topic of landing spaceships. Okay, so that's last time stuff. Yeah, there's a bunch of cool little nuggets in that also. I think that whole convex relaxation thing is a deep topic area that has a lot of connections to other stuff. Super interesting. Okay, so today we're going to talk about how to walk. We're going to dig into kind of some standard, what has evolved into basically the standard approach for making legged robots walk. Mostly quadrupeds. Humanoids are a little harder, but the same approaches can be applied to humanoids as well. It's just that the state-of-the-art results where you're really pushing the hardware on the humanoid side, i.e. Boston Dynamics, they're doing fancier things than this, but this gets you pretty far. And basically all of the quadruped stuff you see from MIT Cheetah to the sort of ETH Zurich animal work, they're all doing slight variations on this sort of setup that we'll talk about today. All right. By the way, who's actually messed with quadrupeds before and looked into these walking controllers? Yeah, obviously in my lab. Yeah, I know you guys, but okay, so not too many other people. This has been a really it's wild actually how fast this has kind of happened. 5 years ago, quadrupeds were still laboratory research. And it's really gone from lab stuff to commercial product you can buy in the last 5 years. Now it's a solved problem. And I think you're going to see these things start to show up in a lot of industrial applications and stuff like that now that anyone can just basically go buy one for a relatively low cost, right? I feel like it's sort of like what happened with drones, but 10 years later, right? Drones went from everyone was playing with them in the lab to a bunch of companies were making them and they become a huge business. I feel like we're basically on the cusp of that sort of transition from lab research to big business, lots of people buying them on quadrupeds too. Anyway, that's all random musings from me that you don't care about. So let's so first I want to talk about a little bit of history of legged robot stuff. Does anyone know, have any guess as when the first legged robots were built? No? I'm gonna take a wild guess.
How do you find a robot?
That's a great question.
Because there was the automatons in the 1650s.
Oh yeah, those were not really I guess I would say self-powered things that can locomote.
They had springs.
Yeah, they were kind of little mechanical clock toy things, right? That were sort of, they moved, but they were
But they didn't have any sensors.
yeah. So I don't know. Yeah, I guess there's a debate to be had about what makes a robot and stuff. So fair. I didn't go that far back. But the first kind of I guess the first earliest work that you could trace a common thread back to from now, I would say is basically in the 1960s. And there's some really wild stuff that people did back then. Some of the first examples were people built these kind of four-legged things that look out of the Transformers that actually a human driver would sit inside and pilot. Pretty wild. So that's kind of cool. And then I would say as a serious academic research endeavor, again, kind of the roots of what you can trace through to today. In fact, the roots of which you could trace straight through to CMU, labs at CMU, labs at MIT, and Boston Dynamics. That lineage very directly traces back to kind of the 1980s. So I would say I don't know, quote, serious research. started in the 80s, about how to, like actually control these things, make them balance, make them, kind of robust, all that stuff that we kind of think about now. And if you go back to the 80s, there were basically two schools of like legged robots kind of in research land. And I'll show you some videos that had like very different approaches. And I would argue we've essentially seen one of them win out in the last 5 years or so, maybe 10 years. The first one was kind of Honda and Waseda University in Japan that had kind of a coupled relationship for a long time that developed some of the first humanoid robots. Really awesome stuff. And this is like the lineage that if you trace it forward ends up with like Honda Asimo, right? Which like 10 years ago was like the state-of-the-art humanoid robot, right? So all that like Honda research stuff kind of dates back to the 80s. And there was the kind of like lineage there and like set of ideas, at least on the control side, and a lot of the way people were thinking about these things was basically a direct translation from like industrial robots, from industrial robot arms, the sorts of things you might see in a Honda car factory, for example, right? That's sort of the idea. And so that sort of thinking of like industrial manipulators permeated all of the design and control on these things. And well, I'll say more about that in a sec. But you can imagine what that means, right? So things like, forward and inverse kinematics, like joint space PD control, impedance control ideas, and kind of feedback linearization type ideas, right? That would be applied to industrial arms were kind of the tools being used. And then there was this kind of completely, I would say, almost opposing viewpoint and school that sort of grew up in the US out of like, I think mostly Mark Raybert, who started at CMU and then moved to MIT and then founded Boston Dynamics. So there's that lineage sort of in parallel historically. And this started out with hopping robots, the famous Raybert hopper, if you've heard of this, and I'll show you guys some videos in a second. And the control ideas here are vastly different from the Honda, like Japanese set of ideas. Like, so those ideas were rooted in these industrial manipulator, robot arm type methods, a lot of feedback linearization, a lot of like trying to cancel out dynamics and sort of torque things around. Whereas the sort of Raybert sort of school started with these very mechanically simple robots with only a handful of degrees of freedom, and is really rooted in thinking about stabilizing the sort of the dynamics of these really highly dynamic motions, like hopping on one foot, right? So there was a big focus on sort of stabilization and balancing, and really interacting more with the natural dynamics of the robot rather than trying to treat the robot as an industrial arm where you like try to cancel all the dynamics out with your actuators. So this led to some very divergent thinking, I would say, across the board, from like the design of the hardware to the control approaches. So these guys really focused on like floating based dynamics and balance. Okay, and then there's sort of, lots of stuff. So, arguably, if you look at where we are today, I would argue that the more like the Raybert school has kind of won in the sort of space of ideas in the last 10 years or so. And that's more or less the school that kind of you can trace a lot of the modern humanoid quadruped stuff to. The sort of Honda Waseda school kind of peaked in the early 2000s with the Asimo robots from Honda, right? If you watch some video, well, I'll show you some videos and then we can talk about what you see, right? Yeah, cool. So let's go look at some stuff. Let's pull up some of the videos and talk through this stuff. So let's start with maybe the Honda stuff. So here's that stuff. So this is early 80s. So this is one of the very early Honda robots. Like this might have been the first humanoid, like early 80s stuff. And if you watch this thing walk, and actually if you zoom forward 20 years and watch Asimo walk, you'll see some commonality. So this is untethered walking, right? This is pretty impressive. But if you notice, the knees are always bent, and this has this classic look of what you think of when you think of like robot, right? Like motion. If you say this thing's walking robotically in this kind of stereotypical way, this is kind of what you imagine in your head when I say that, right? And it comes down to like this thing is always has knees bent, and it has big fat feet. And if you watch what's going on, they're basically treating this thing as like quasi-static throughout the gait. And in particular, it's set up in such a way that you're basically treating the whole robot as a fixed base manipulator, like an industrial arm, when the foot's in contact. So it has these big, gigantic feet, so it has a big contact patch, and it can balance on one foot. And it's making sure that the knees are always bent so that it never encounters any kinematic singularities. And you're basically switching from modeling it as a fixed base manipulator with this foot on the ground to a fixed base manipulator with this foot on the ground. And that's the whole deal. And most of the control methods are based on the same exact ideas you use for an industrial arm, where you're basically doing like really beefy torque control and like feedback linearizing everything. And you're taking advantage of the fact that the thing's fully actuated when the foot's planted, right? But again, yeah, watching these things move around, you kind of can see this like robotic quality to the motion, right? That kind of comes again back to the fact that they're relying on a lot of model simplification and really beefy actuators and modeling this thing like it's an industrial arm bolted to the ground. So it can only really do motions that sort of, stay within those assumptions. Okay, so that's that end of things. Now let's go watch the Raybert stuff. This was I think this was at CMU or MIT shortly after. You can see this is the original Raybert hopper. So this is like a wildly different conception of how these legged robots should operate. These guys started with these really, really simple hardware designs, but got at these core sort of dynamics and control notions of like balance and stability of like a highly dynamic, under-actuated platform, right? So they did hopping, and then they put, basically two legs together and did running gaits like this. And you'll see more of this in a sec. And you'll see, like, this was all like, again, in pretty early 80s, and blew everyone's minds, right? When they were doing stuff like this before anyone ever thought stuff like this was possible. You'll see some pretty nuts stuff too. So jumping, there's a backflip in here. Yeah, there you go. What else? Yeah, running untethered on a, so this is now in 3D, right, on a treadmill. Pretty awesome. Oh, these are just fun to watch. Super cool, right? So they kind of, and then they chained more of these things together and came up with like quadrupeds. So this is like a nice quadruped running down the hallway. Different quadruped gait. Anyway, super cool. And this basically, yeah, the story from here, right? So Mark Raybert ended up, started here, went to MIT, then spun out Boston Dynamics, and that story up to the present day. All right, cool. So that's that for now. Put this back away. Okay, so that's some history. And let's try to, I would say then like kind of where we are now, just to sort of like zoom forward a little bit. It's working, yeah, cool. So like the past, say 10 years or so, there's been a ton of work on the mechanical side. And this has been equally important, I would say, to getting these things to work in practice. In particular, there's been like in the last 10 years, there's honestly been like a revolution in actuators for robots. Like motors have like completely changed in the last 10 years, and this is a big part of the story. Essentially, we went from like 10 years ago having these complicated geared transmissions all over the place to now most of these dynamic robots using direct drive motors, which make a huge difference in the capabilities in getting these dynamic motions out. Pre-direct drive motors, and actually, if you look at Atlas, which the development process for that started long before this direct drive motor kind of revolution, Atlas has hydraulic actuators. And the reason is, pre-direct drive motors, you kind of couldn't do a lot of this stuff with geared transmissions and motors. And so they went with hydraulics. But really Sungbae Kim at MIT, who did the Cheetah robots, he was kind of the guy that really pushed this direct drive or quasi-direct drive motor thing. And like part of the story of getting Cheetah to work was they actually developed their own motors to enable a lot of that stuff, so that's a very important piece of the puzzle, and one thing that has really come a long way in the last decade or so. They haven't, but I think like, if they wanted to, build a quadruped that could do this, they could. And like Spot is really trying to be a commercial product, right? They're like, trying to make that thing, able to go out in all kinds of weather, every day and work super reliably. Whereas Cheetah is a research platform that has to work well enough to like bang around in the lab and get a cute demo video once of the backflip, right? So they're very different things.
But didn't see Spot running like the one that in the development phase that they were doing, like running at high speed.
I mean, I don't know that they cared to do that. So Spot is also a direct drive motor. It's not hydraulic. I don't know what that was in response to. So yeah, Atlas is hydraulic. Spot is a much more recent design and does motors. But yeah, I think Cheetah, was a research platform in the lab trying to do cool things, right? Whereas Spot is trying to be an actual commercial product that they can sell to companies for inspection tasks or whatever that has to work, under all kinds of conditions repeatably forever, right? With low maintenance. They're very different ends of the design spectrum. So, I don't know that I would read too far into that. They're not trying to be the same thing. Okay, so there's been a lot of work on that stuff, and that has really changed the game. And then the other piece on the control side has been huge advances in model predictive control, which is a lot of the stuff we've talked about here. And that's a big part of the story for all the recent quadrupeds that have worked successfully. Cheetah, Animal, Spot, etc. And also humanoids, right? And all the BD Atlas stuff is also kind of really pushing the envelope on the NPC side. Okay, so that's a little like whirlwind historical overview. Now let's try to get into sort of how this thing actually works. So we're going to go over like roughly speaking the Cheetah control stack, modulo some details that vary a little bit, but the big picture idea. So first, let's start off with kind of the high level sort of full stack picture on this thing of what the control loop looks like. So as usual, we've got like some state estimator. This feeds into, in this case, this is a kind of a funky, setup. So we've got a sort of gait / footstep planner, and we'll talk more in detail about all these things, but just kind of illustrate what this looks like. This thing then feeds into two things. So we've got an MPC controller. So we'll call this the body MPC controller. And also a joint controller. So this goes up here also. And then this gets run on the actuators. So that goes on the robot, and then the whole thing feeds back Okay, so cool. So let's talk about what goes from what block to what. So from the state estimator, we've got position and attitude, basically. Then we have this gait / footstep planner. The reason for this is that this is basically doing the hybrid sort of stuff that we talked about when we talked about contact. So we're assuming that there's some fixed gait or set of footsteps that's coming out of this planner. And this is usually done with some heuristics. There's like a whole literature on different heuristics here. We'll talk a little bit about this. So this thing is going to spit out basically contact mode information, which we've talked about, right? And that gets fed into the MPC controller in the form of constraints over the MPC horizon, right? For what feet are on the ground at what time steps. It also generates a set of swing leg trajectories for the legs that are not in contact, right? So the MPC controller only knows about basically the feet that are in contact at which times. It doesn't really reason at all about the swing legs, right? When they're not on the ground. And so that is where this joint controller comes in. So we also have these swing leg trajectories, which typically are just made up. So it's common to just define them in terms of some polynomial spline or whatever that you make up. And then this joint controller takes that swing leg trajectory information and the body force and torque from the MPC controller, and then computes actual motor torques, right, from there. And then that all kind of gets fed back. You've typically got like an IMU on the body, maybe you have vision, joint encoders, whatever, and that all goes into a big state estimator on the other side, which is typically some kind of extended Kalman filter. There are lots of papers on that too, but that's, you know, more or less straightforward. Okay, cool. So let's see. Sensors that you would typically have, joint encoders, IMU in the body. Typically, you also have some sort of contact force or flag sensors on the feet. These can be a lot of different things. A lot of the current low-cost quadrupeds have pressure sensors in the feet to try to get some force information. It's also in some designs, they just have a switch to detect if the foot's, it's like a binary flag, right? If it's in contact or not. So there's different ways to do that.
Wasn't one of Cheetah's advances that they just used the back EMF on the motors?
Yeah, you can do this too. There's been a lot of work on lots of different ways to do this. What this all comes down to is you need some way of actually measuring whether your foot is in contact or not in a robust way. You're kind of like using this gait planner, right, to sort of in an open loop way specify what's going on with the contact modes. But that's extremely brittle, right? If you're on any kind of rough terrain or whatever, the timing's not going to match up. And so you need some form of feedback on that mode timing. And the way that practically happens is by using these, like some method for detecting contact. So yeah, you can do it with back EMF in the motors. You can do it with various types of foot sensors, which are common. We've got a recent paper now in our lab where we're using IMUs in the feet, which actually is very cool and lets you, in addition to estimating just normal force contact, actually estimate slip as well. It's pretty slick. So there's lots of ways to do it. But generally speaking, you need some way of inferring this foot contact information, whatever that is. And then if you're doing stuff kind of outdoors, you know, and you need to navigate, it's also pretty common to have vision or GPS in there somewhere to do global kind of pose estimation. Okay, so that's that. The state estimator for these things, as I kind of mentioned, these are basically always some kind of EKF. There's a kind of, you know, decent sized literature on this stuff as well, with lots of tricks, mostly around how to handle contact. And in a lot of cases also foot slip. So yeah, this comes down to like the EKFs are generally also doing hybrid-ish things and having to reason about the foot context. So having an explicit context sensor on the foot allows you to just like, switch the mode in the controller and the estimator as soon as that contact flag goes, right? Otherwise, yeah, there are other ways to do it, but they all are a little fuzzier sometimes, and that makes life harder. What else? Okay.
Protect the sensor that you,
Sorry?
how do you protect the sensor like the IMU at the tip of the
So the pressure sensors, so usually these things have rubber feet. A standard, for example, the unitary quadrupeds that are fairly cheap in all these labs right now, the way they work, they have like a molded foot with an empty cavity inside. Basically, it's hollow. And they have like a barometric pressure sensor in there. So when the foot compresses, it compresses the air inside. And like you get a pressure measurement in the pressure sensor. So that's one way to do it. In our case, I mentioned the IMU thing. We mount the IMU directly above the rubber foot on the actual metal link. But yeah, lots of other ways to do this. Many ways to do it. You need something in general, right? Let's see. Okay, so that's state estimator. Then we have the sort of gait / footstep thing. And this thing is planning foot placement / timing and swing leg trajectories, as we mentioned, based on some pre-specified stuff and some heuristics. And typically also the desired body velocity is in there as well. There's also like very often extra heuristics in here for like push recovery and things like this. So these can get a little kind of like spaghetti code, and this is where there's a lot of voodoo, I would suggest. Okay, so that's that stuff. Then we've got the MPC controller, which is where we're probably going to spend most of our time. And this is kind of fascinatingly simple. And essentially, these guys treat the robot as a single rigid body. And assume that that the feet are at, kind of wherever the gait planner says. And the output of this guy is a set of contact forces. For the stance feet. All right. And then, yeah, finally, that joint controller. This thing is, actually generates motor torques. So the MPC thing spits out desired forces for the stance feet. So it figures out the joint torques to get those ground reaction forces. And then this gait thing spits out these swing leg trajectories. So it also then figures out the torques to generate the desired swing leg motion. Okay, so that's roughly this outline block diagram thing. Any questions about that? How this thing's set up, what the blocks do? Okay, yeah.
Where would you see the biggest change?
Yeah, so the thing that gets, so the biggest kind of, or one of the biggest assumptions here, there's kind of two big assumptions in here. One is this like hybrid setup where you have this gait planner, right? And that lets you kind of decouple a lot of things and do this hybrid stuff. So that's a big one. And so that definitely changes, right? On a biped, that looks a little different. But in general, like most of the successful controllers are still doing this hybrid setup with some separate like footstep planner for the humanoid, but that'll definitely change on a biped. Then the other thing that's tricky here is this NPC controller is using this single rigid body model, right? In quadruped land, this is a reasonable assumption. And in fact, people have built the robots to more closely follow that approximation by making the legs as lightweight as possible. So on most quadrupeds, the motors are actually up in the body and they're connected through transmissions of various kinds into the legs, right? But the legs are really light. And, the typical quoted heuristic, like for cheetah and stuff, is that the legs are about 10% of the total mass, like all the legs added together, about 10% of the total mass. So now, modeling it just as the body, pretty much as a single rigid body, is pretty good, right? It's like a 90%-ish of the story. On a humanoid, though, that's generally a much poorer approximation. So like, generally speaking, on a biped, you've got much more massive limbs that account for a way more of the total inertia and mass of the body. So if you're swinging those heavy limbs around, now that's having a much bigger impact on your dynamics. And this decoupling assumption where you basically take care of all the swing legs stuff, separately, and that's not at all accounted for in the NPC controller, is a much poorer approximation, and you kind of can't get away with it anymore in a lot of cases. People try, but if you do this when you have big inertial limbs now, it means that you're ultimately having to very dramatically limit the performance of the robot, i.e. you're not able to like do super dynamic motions or whatever, because you're going to have to move relatively slowly to not break these assumptions, right, of like the single rigid body model and stuff like that. So that's, I would say, the biggest thing is like the mass of the limbs is much more in a biped typically. And so that NPC setup with the single rigid body model is no longer very good.
This is called the centroidal.
So you can call it centroidal dynamics. That can mean something a little more sophisticated though as well. So centroidal means that you're using a sort of a single rigid body model that basically the centroidal dynamics are they're the momentum dynamics of the robot. So if you were to like add up all of the linear angular momentum of the whole robot and write those dynamics down, that's what the centroidal dynamics are. That's what a centroidal model is. But that in general, that does account for the inertial effects of the limbs, right? So like if you were to write that model down, it would include like the instantaneous and like time varying inertial effects of the limbs, right? So here we're not doing that. So this, people call this centroidal dynamics, but there's sort of various flavors of that, and people can mean slightly different things by it. I'd say the most like rigorous definition of centroidal means that it's the momentum dynamics, which do account for limb motion.
Like in which cases will be like the momentum dynamics, and which cases will be like the normal forces or mounting that way.
So here, right, what we're doing is ignoring the inertial effects of the legs and just modeling really as a single rigid body. That's commonly called centroidal dynamics. Some people call it the potato model. I think that might be a more accurate description. But you'll see actually, like for humanoid robots, for example, where the leg inertias matter a lot, you'll see people write down more sophisticated versions of this centroidal dynamics that actually do account for the instantaneous inertia of the full robot. So what I mean by that is like, I might not be writing down all the joint space dynamics of the whole robot, but given a joint configuration, like my inertia standing like this is different than my inertia standing like this, right? And those centroidal dynamics account for that varying inertia.
Is it also called shape accelerator from the shape?
I don't know, you can call this lots of different things, but my point is, right, the centroidal dynamics can mean more than this very simple single rigid body model. We are ignoring the inertias. It can mean this sort of thing where you're writing down the total momentum dynamics while accounting for the inertial effects, but you're just not accounting for all the joint space stuff, right? So you're not modeling a level of joint torques. You're modeling at this funky sort of like, kind of lumped inertia level, but you are accounting for the fact that the inertia is changing in time as you move around, if that makes any sense. So yeah, there's papers.
There's a mass distribution happening, then we should go for momentum. instead of this.
Yeah, so this is, I would call this a single rigid body model. That's maybe, or potato model, which is a lot of people call it. I think that's a more accurate description than centroidal dynamics, which can mean something else that's a little bit more sophisticated. And there's papers that do centroidal dynamics with full joint kinematics. So what that means, right, is you're not modeling the joint space dynamics at the level of like motor torques and stuff, but you're modeling like the kinematics of the robot, like you're modeling. So if I'm walking, for example, I would be taking like, for example, this scheduled gait, right, where my legs are moving, and I'd be modeling the inertia of the robot over that gait as changing in my dynamics, right? So it's not a single rigid body. It's this kind of weird lumped inertia model, right? That accounts for the inertia of the whole robot, but not the joint space dynamics, if that's really what centroidal dynamics means. Okay, that was a long sort of, if you're curious about this, I can send you a couple papers, but that's sort of, there's a subtle difference. And I think again, the accurate description of this is single rigid body. Okay, cool. Everyone good? We're going to get into that. It comes down to this description, this decoupling, because they have this kind of, gait planner thing separated from the MPC controller that's only reasoning about the body. They're totally like the controller, the MPC controller that's actually, reasoning about the dynamics, doesn't know anything about what the legs are doing really, other than what feet are in contact. So typically you're running this like you're basically running this gait open loop. So like in a typical controller like this, you'll have like a selection of like trot or gallop or whatever, right? Some gait. And that gait pattern just gets run open loop by this gait planner. And the MPC controller is running on top of that. So yeah, if you're not moving, it's still going to do the gait. This is a very common thing. Yeah. And right, it doesn't make a lot of sense, right? You'd think like if I'm sitting still, like my legs don't need to be moving. But if you look at a lot of the controllers, because of this decoupling assumption, the gait sort of exists totally separately from like any sort of task level objective in the controller, right? So you don't really need to stand there trotting in place, but the controller is going to do that because you've decoupled that trotting behavior from the sort of any goal directed behavior in the controller, right? Yeah. Yeah, I mean, that's all this gait footstep planner thing. So like you can imagine, you could switch between two gaits in that planner. This is very common. Like if you actually drive one of these things around, typically the controllers have like a thing where you can select a gait. You can pick a trotting gait, a gallop or whatever. There's lots of these, right? So you can literally like select those from like a drop down thing or something, and then it'll do that gait, and then you can drive it around, And when you drive it around with the joystick, ultimately what that's doing is feeding like a desired velocity command, into the MPC cost, right? So you can switch between gaits. You can also like this gait scheduling thing. What that generally means is again, the mode timing, like into the future, right? So that's all that gait footstep planner block. There's lots of papers on this, lots of heuristics for deciding which gaits to use, and like all kinds of things like that. All right, anybody else? Okay, keep trucking. So that's that. So let's like talk a little bit about the dynamics then. So we have a state vector. So this, we're gonna we'll write out kind of the general story and then like kind of how some of the simplifications happen. So state has configuration or pose, which is Q, and then velocity V. And in the case of one of these legged robots, if we were to write the full body dynamics down, it would look, the pose or the Qs would look something like you'd have body position, body attitude, like a quaternion or something, and then joint angles. And then, something like, not exactly maybe, but, something like V equals Q dot, or, some Jacobian times Q dot, right? And then we're going to write down manipulator dynamics. So hopefully most of you guys have seen this before, but maybe some of the ECE types have not. This is just like standard way of writing down dynamics for robots. It's equivalent to like F equals ma or the Lagrange equations or whatever, if you haven't seen this. we've talked about it a long time ago. And I'll kind of like walk through what these terms mean. Okay, so we've got mass matrix. This was, I think I did this the first week of class, so just as a refresher, because it matters here. This guy is sort of your Coriolis and gravity sort of terms. And then here, this is called your input Jacobian. This is the thing that maps your control inputs into your dynamics. Right. This would be, in general, your joint torques. Then this is what we call the contact Jacobian. And kind of really similar to the way that the B matrix maps your control inputs into your sort of generalized coordinates. This guy maps your contact forces into your generalized coordinates. These are contact forces. Okay, then we'd have, sort of the interpenetration constraints, like we've talked about previously. So this would be something like your sign distance function having to be non-negative. And then we'd have our friction cone constraint also, right? So this, I'm going to write it like this and talk about this. So this is assuming that these Fs, this is per foot, but looking at it, if it were just like 1 foot, you're right, this F is a 3D vector, and we're assuming that it's written in such a way that its first component is the normal, and then its second and third components are the tangent components, right? So the normal force is F1 on the right there, and then F2, 3 is the tangent friction forces. And this, we wrote this down before, right? This is like basically the Coulomb model. Mu is your friction coefficient. Okay, so this is the whole thing, right? So if I were to write down a simulator for the quadruped where I wanted to do like the whole full body dynamics thing, this is pretty much what I'd do, right? This was what it looks like for the whole thing. And I would then kind of discretize this somehow and simulate it, right? So this is like roughly what's going on in your simulator. That said, this is very complicated, very high dimensional, and very messy for doing real-time stuff. So this might be what you do in your simulator, but this is typically not what people are going to do inside the controller, like in the MPC controller, because it's too complicated. Okay. So this is big. Yeah, the state dimension is fairly big. So like typically this would be, say like something like, 36 dimensions or more. And the other note here is that trajectory optimization stuff, right? All the stuff we do scales cubically in that state dimension. So being, twice as big means it's 8x more expensive, right? So it's a big win in terms of compute and solver speed and all that to make the state dimension smaller, right? It's not like it's a cubic win. If you can have the state dimension, it's like almost an order of magnitude faster. So that's a big deal. So all of these things are kind of pointing us in the direction of like simplify the dynamics. And finally, this is all highly nonlinear, right? Which makes life harder. Okay, so that's that. So now we're going to look at what variously called centroidal dynamics. Yeah. This is how far so in the simple case here of like, if we're looking at the foot of the robot, This is how far the foot is from the ground. And it's positive if you're above the ground, and it goes negative if you're below the ground. And so that's the signed part. And then the constraint is that that signed distance has to stay non-negative, right? If it goes negative, it means you're through the floor. Make sense? Cool. Anybody else?
Time distance is 0 on the ground.
It's 0 when you're in contact. It goes negative if you're through the floor. If you're penetrating, it's positive if you're out of penetration.
So when you have a rough ground, like, how will you model that? Like,
Yeah, so you can always define it, but it might be non-trivial to compute, and it might be non-smooth in general. But what it's defined as the closest point. It's the distance between closest points. So if I had like some complicated, crazy terrain and my foot was here, I'd actually have to solve, in general, I'd have to solve an optimization problem, right? To figure out what the closest point was on the terrain to the foot. And then that would be what that thing is. So in general, it's defined as the solution to this like minimum distance problem, which in general is non-convex, non-smooth, right? You can imagine if I have something with corners, the solutions are non-smooth because they can jump between corners and stuff. So it's, in general, that function's not nice. And that's part of why this is hard too. It gets nasty. And this is like yet another reason we don't do this in general. There's actually a large literature on computing signed distance functions. It's a non-trivial thing. So it's not a bad question to ask. Like in general, that's a messy thing to do. In fact, I just like read a paper this week about like, using like crazy neural net stuff to try to compute signed distance functions quickly, blah, blah, blah. It's messy. So yeah, good catch. Okay, so that's that stuff. So now what we're going to do is write down like kind of the dynamics that are typical inside the controller, inside the MPC controller. And so these are maybe called centroidal dynamics, right? We'll call it like single rigid body. Okay, so here's what we're going to assume here to do this. Yeah. The like complexity of solving generally the complexity of just doing dynamics is cubic in the state dimension. But yeah, also like trajectory optimization is cubic in the state and control dimension and linear in the time horizon. So we talked about this when we derived like LQR and DDP and these things. It comes down to like the size of the matrices that you have to invert. So you can imagine doing the backward Riccati recursion for like DDP or LQR or whatever, the sizes of the matrices in there. So first of all, it's linear in the time horizon. That's just because you do the same operations for sort of big N time steps, right? So the more time steps, you just do the same stuff more times. So that's linear. Then if you look at the sizes of the matrices, you end up having to invert a matrix that's the size of the controls, right? That like R thing has to get inverted. Matrix inversion is a cubic operation. And then you end up having to like multiply and look at matrices that are the size of the state dimension, like the cost to go Hessian. Matrix multiplication is cubic in the size of the, right? So basically there's cubic operations in both the X dimension and the U dimension. Does that make sense?
Yeah.
So that's where that comes from. And so, yeah, you can like analyze this in terms of computational complexity, blah, blah, blah. But the bottom line is you need, order N cubed floating point operations in the state, M cubed in the control, right? To like compute one step of DDP or Riccati or whatever. And if you're clever about the sparse matrix stuff in Dirkall, it scales the same way. Anybody else? Okay, cool. So here's what we're going to do. So the first one, which we've already kind of talked about this, you assume that the legs are very light. So the leg mass / inertia is much, much less than the body. In general, like, the standard kind of number is about 10% for something like cheetah, a lot of the quadrupeds. And then the other one is that the leg actuators are very fast compared to the body motion. So the gist is that you can like, for like the swing legs, for instance, you can basically put that foot where you want it, when you want it. Basically, I can move the swing leg really fast. I can move the swing leg much faster than the motion of the body. That's really the assumption. which you can imagine becomes very important if you're trying to do like push recovery, right? I need to make sure I can like stick my leg out and catch my fall, right? Okay, so then with those assumptions, we're going to use a sort of lumped single rigid body model for the whole robot. So the sort of translation dynamics are just F equals ma. So we've got something like, mv dot equals minus mg. So we got gravity. And then we're just going to sum over all of the ground reaction forces. So these are sum of contact forces, right? So we're just doing F equals ma, adding up all the forces on the robot, gravity and contact forces, that's it. And then we do the same thing for the attitude dynamics. So we've got kind of our Euler equation stuff, j omega dot plus Coriolis term, so omega across j omega equals, and then here, this is just the sum over all the torques. And for the only torques on the robot, right? Gravity doesn't exert torques. So you've just got the ground reaction force stuff. And that looks like R cross F for every foot. So we're going to just write it like that, R cross Ri cross Fi. So this is total torque. Actually, let me move this. So we've got, this is total torque. This is foot position. Right, so tau equals R cross F. Let's do with that, right? Yeah. So these R's are the foot position, like relative to the center of mass. Like you just felt that, right? To be clear, right? When I write Euler's equation, it's all in the body frame, right? So the torques are also in the body frame. So yeah, that's got to be that way, right? Yeah. Okay. And then lastly, we have kinematics. So you've got something like R dot equals V. And if you're using a quaternion for your attitude, which you should do, but apparently no one had really done for these quadruped controllers, apparently, because we just did it in like the last few weeks in our lab. And apparently no one has published this before. So whatever. But if you're being like a reasonable human and, using quaternions like a sane person, you'd get this. But that said, yeah, most of the existing stuff uses Euler angles. Just sad and terrible. Okay, so then kinematics-y things, right? Okay. Yeah. Okay. So that's sort of, yeah.
In my Cheetah 1 paper, used the virtual impedance controller. Is this and Gait over that, or is it a different part?
That's a different part of the stack. Yeah, that's sort of the lower level leg control stuff. So this is like what's in the MPC controller. Does that make sense? Yeah. So there's lots of variation on that lower level joint controller. That's actually, this gives you like ground reaction forces, right? And then you have this like joint space controller that's actually like taking this and turning it into motor torques and also like doing the swing leg control. There's lots of variation on that. And that's where you see stuff like maybe impedance stuff, maybe just kind of very simple, so that's a different thing actually. That's something called that's another walking model, the inverted pendulum stuff. But yeah, you can see, like you sometimes see actuator allocation things where you solve a QP to get these forces. There's all kinds of variations, right? Okay, so but this is the single rigid body or centroidal model, right? It's still nonlinear. So what is standard, we're gonna like start making some more assumptions to try to get to a linear model. And this is sort of consistent with the theme here of like linear models are good if you can get away with it. And you can go really far with convex / linear MPC ideas. So here's what they do. So first, I guess we're numbering these sequentially. So assumption 3. So if you assume the body angular velocities are small, then you can get rid of the omega cross j omega term in the attitude dynamics. Right? That's a quadratic term. So it's omega squared. So you can ditch that if omega is small. The next one is you can assume that the body pitch and roll are small, which is pretty reasonable assumption if you're walking on relatively flat terrain and stuff like that, right? If you're not doing like parkour, that should be true. Yeah. J is the inertia matrix for the robot defined in some coordinate frame of your choosing, like whatever body frame you like. No. A single moment of inertia is defined about an axis. If I want to like write down the inertia for an entire body, that's a matrix or second rank tensor. That's the inertia matrix, right? So that encompasses the inertia about any axis in the form of a matrix, right? Yeah, exactly. So from that matrix, you can back out the scalar inertia about any axis you want. That makes sense? Yeah. Yeah, so this in this Euler equation, guy, the j omega dot plus omega cross j omega equals torque thing, the omega cross j omega term is like a quadratic term, right? It's omega times omega, it's got an omega squared thing in it, right? So that, if we're gonna say omega is small, then that's squared small, right? So it's very small, so we get rid of that when we linearize. Cool? Anybody else?
Like a gallop, do you just turn the MPC off, like for the part that's in the air? Like what's it even doing?
No, because what you need to do, right? If I get like slightly perturbed and I'm in a flight phase, I can't do anything about it, right?
Right.
So what ends up happening is the MPC is planning ahead over a couple of gait cycles. And what it's doing is saying, okay, well, I'm in the air right now. I can't do anything right now, but my body's like rolling sideways and that's bad. So what it's doing when it's in the air is it's figuring out, okay, well, when my next foot strike happens, I need to do this and this to like sort of correct and balance myself out, right? So that's the MPC thing, right? It's planning over this horizon. In the case of these like legged locomotion examples, you almost always need it. Like you can actually like kind of, there's some proofy things you can get it at, but in general, like a good heuristic is you need like 1 to 2 gait cycles of horizon to make this work, actually, to get it to stabilize. Because what it's doing is looking ahead over the next gait cycle saying, okay, well, I can't do anything right now, but if I look ahead far enough, my feet will be in contact in the future. And given where I'm at now and where I think I'll be that far ahead, here's what I should do in the future with my future foot stuff, right?
So the horizon's further than then I guess if we did just have like the beefiest nonlinear MPC solvers running when we took the legs into account, then we could have actually better performance because then
Absolutely,
or something we could like take it. We could use the inertial.
Yeah, exactly. So yeah, you could maybe think about like, doing weird falling cat things in midair where you wiggle your body around to reorient. So absolutely, yeah. So if you were to like pull out all the stops and model everything, you absolutely can get more performance. Yes. But that said, there's the interesting thing that's happened in this space in the last decade or so is that there's been this strong coupling between hardware design and control developments where people have actually built the robots to better reflect these approximations you're making in the controller. Nominal, like, for example, people have like concentrated all the actuator mass in the body and used linkages to get the legs to be super light so that it was a better approximation, right? On a lot of these robots, right? Which, is a choice you're making for this reason, right? Like you could have put the actuators in the legs, right? But that would have made the legs heavier and would have made their inertias matter more, stuff like that. Okay, cool. So the next one here is we said body pitch and roll. And then last one is that the foot positions track the reference really well. So like,
I'm sorry, what's the result of the body control also?
We're gonna write that down in a sec, but where it shows up is in these kinematics, right? So it's specifically those quaternion kinematics. Those are like bilinear, right? Or they're nonlinear in Q and omega. If your state has both Q and omega, that's nonlinear, right? So by making these small pitch and roll assumptions, what we're basically going to do is linearize about the pitch and roll axes, but not the yaw axis, right? So the idea is you can have large yaw, which is standard if I'm like doing this, right? But I'm not doing like a backflip. So those other two angles. So I can linearize about 2 out of the 3 sort of orientation angles. Okay, so that's that. So if I take all of this stuff together, I get down to some really simple looking stuff. So this doesn't really change because this was already linear. So sum over, but now this guy is going to sort of simplify down to look a lot closer to what we had up there. I'll write this down in a sec. So we get rid of the omega cross j omega term. And on the right-hand side, this thing is sort of an input Jacobian thing that looks like, so we talked about, when we did all this quaternion stuff, we talked about this like hat map idea, this like cross product matrix thing. So that's what this big R is. It's basically a bunch of these cross product matrix stuff. But the important thing, and the reason I wrote it like this, is that it's computed once using the reference. So this is kind of where, again, this linearization stuff comes in, right? So the way I wrote it up here, it's R cross F. That R is a function of the state, right? So that's nonlinear in my MPC setup. What I'm doing down here is for a given like reference, I'm going to compute that R cross thing once, evaluating it about the reference, and I'm just going to plug that into the MPC like that, so that the R's are fixed. They're not state dependent anymore. And that way I've linearized that R cross F term. Yeah. So the idea is, if I were to, right, if I do the version up here, that R is a state dependent thing. What I'm going to do down here, though, is if I assume that the legs are exactly tracking the footstep plan from the footstep planner, like that thing has all this like weird gait pattern stuff. It's got the swing leg trajectories, blah, 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 right? So that thing like is nominally telling me exactly where the legs are going to be, right, ahead of time over the MPC horizon. So what I basically do is I take that nominal like leg trajectory footstep plan from the footstep planner. I basically roll it out over the MPC horizon and say that's what's going to happen. And then I use that to evaluate the R crosses over the MPC horizon and just throw them in there and assume it's fixed, right? So this is assuming that you're tracking that like footstep plan pretty well, right? At least over an MPC horizon or whatever, right? You're doing this, you're running this right in the loop quickly, so it gets reevaluated. So if something gets messed up, you're gonna like, tweak it, change that, and the next MPC solve that might change, but that's kind of how you get down to a linearized dynamics here. You're gonna just assume it follows the reference, right? Okay, and then kinematic stuff, like we said, this position/translation stuff, super simple already, but then we're gonna, using the small pitch and roll assumption, we're gonna basically get something that looks like this. So we no longer have the complicated quaternion kinematics. Instead, we're going to use a 3-parameter attitude representation. So something like, say, roll, pitch, yaw. Angles, something like Euler angles there. Okay, yeah.
If you're assuming the actual position is the reference position which having are how would recovery behaviors wouldn't be mess up?
Yeah, so it's going to be wrong in general, right? And you're going to kind of rely on fast replanning to take care of stuff like that, right? So if I get a big disturbance, my footstep planner is going to change, right? So like like this is where, there's a lot of literature on these like footstep planning heuristics. So if I get knocked really hard, what's typically going to happen is there's some push recovery thing that's going to happen. And that footstep planner is going to like plan some new footsteps, right, that are trying to do the push recovery thing. So like, that'll go into the next MPC solve, basically, right? So you're depending on the fact that you're resolving this at high rates to get at those kind of behaviors, right? Okay, so with all of that, now I get a linear state space model that looks like the following. So I've got something like this. This is my X dot. And I've got a big A matrix here that looks something like, it's really simple. It's like a integrator dynamics. And then I have a B matrix down here that's got a bunch of identity things for the forces, and then a bunch of these R's that have those like R cross things for the torques. And these are your contact forces. So if I'm like, writing this in linear systems lingo, this is X dot equals A X plus B U. So we have a nice linear system, which is kind of insane that we went from this like super gnarly, complicated multi-body system with contact dynamics, blah, 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 to something that looks like X dot equals AX plus BU. It's kind of insane. Like, you shouldn't be able to do that, but that's sort of the clever, stuff that makes this stuff work. Okay, so that's the MPC thing. And just a quick, like, kind of sort of word about the footstep / gait planning stuff. So what this thing is doing is specifying foot contact mode timing. And one way that this gets done, and one way you can kind of visualize this, is with like a mode plot. So you can imagine if I plot the foot contact mode as like a binary thing versus time, and I stack up, say, like the front left foot, front right foot, back left, back right, right? I might get something that looks like, something like this, right? Where I get some, so this might be like one gait cycle, right? And then it repeats. So I've like, sort of have varying combinations of feet on the ground at different times. This, I just made this up. This is not accurate or representative of anything, but you can imagine like various pictures like that, basically can specify, a trot versus a gallop or whatever, right? Based on the sort of timing and the overlap of the feet being on the ground. Says when to put the feet down. Then there's this sort of, so that says when, right? Doesn't say where. So how do I figure the where part out? So there are more fancy versions of this MPC setup where you actually put the foot positions into the MPC problem as decision variables. So the timing is still assumed, but the MPC controller can decide where to put them. So that's a thing you can do, but then it becomes more nonlinear and harder. So there's another way to go, which is the classic thing. So let's, there's this kind of standard thing called the Rabert heuristic. Who's heard of this before? Everyone in my lab. Okay, fair enough. It's very intuitive and kind of one of these like genius little insights. So the idea here is, so I have my foot position, say, and I'm going to set this equal to the hip position of the robot plus, if I have like some gait period, call it delta t. So that's like the gait cycle time, right? I'm going to take the velocity of the body and say, so if here's the hip position, right? And then here's the foot position. I'm going to put my foot a distance out in front of my body right now when I put it down. That's basically V over 2 times the gait period. So the idea is I'm going to stick it that far ahead of the hip joint such that over a gait cycle, you should get a symmetric gait, right? So that's putting it so if I were to integrate the velocity over a full gait cycle, that'd be V body times delta T, right? That's how far I'm going to move over one gait cycle. So the idea is I reach out half that distance. So when I put the foot down, it's half a gait cycle travel distance ahead of me, so that when I pick it up again, it's that same distance behind me, right? So this heuristic basically sets up a symmetric gait pattern where you sort of put the foot down and then lift it off the same distance ahead of and behind the hip joint. Does that make sense? So that's where it comes from. It's a very like nice, intuitive, simple idea. It's kind of a pretty, thing, but it's, again, at the end of the day, it's a heuristic. It's made up. But this is a very, very standard thing to do. So let's see. These are both. No. The assumption is that like what you're doing is you're deciding, assuming a fixed, forward velocity of the body, say, what you're saying is that the sort of like the swing leg motion is symmetric. So I'm like, the foot is on the ground, sort of the same distance ahead of and behind the hip joint, right? Over a gait cycle. That makes sense? Yeah.
Does work even when they have to be ready?
Yes. Yep. So yeah, to be clear, these are the positions projected onto the ground, right? And it does work in the 2D case. Yeah. Okay, cool. So far now we've got timing and where to put the foot down. Again, there's other ways to do this, but this is like a very standard approach. So now the next piece is, what do we do? So this is all about the stance feet right now, right? So then there's this last remaining thing of like, what do I do in between the stance phases? Like, what do I do with the swing leg? So we have this question of how to swing the leg between stance phases. And the sort of standard approach, like, again, you can do fancier things, right? But in one of these sort of very decoupled MPC stacks, a standard thing would be to use basically a hand-designed spline curve. So like a cubic spline or something like this, that you trace out. That's just made up. That you then track with like a joint space PD control. So this might look like, so if these are the joint torques, you might have, so this would be like your swing leg kinematic Jacobian, and then you'd use like a PD control in here. So this would be a scalar proportional gain. This would be your foot position reference, foot position tracking error. And then you'd have a derivative gain. And then this would be your like velocity of your foot position tracking error from that spline curve, right? One of the reasons you write down a spline curve is those are easy to diff, right? If I have a nice cubic spline, I can take its derivative analytically. So it gives me an R dot that's also well-defined. So I can plug this all in. This is foot position. This is swing leg kinematic Jacobian. These are joint torques. There's also fancier ways to do this, right? But this is kind of the most basic, simple thing to do. And then part of the assumption is that the tracking here is very good, right? You're basically assuming that that stance foot's going to end up in the right spot at the right time. the MPC controller is like assuming all this, right? So you're kind of assuming that this tracking is very good. Okay, so that's most of the puzzle. And then the last piece finally is the MPC controller itself. And the idea here is you're trying to track some desired body motion. The horizon, as I kind of just said before, is typically 1 or 2 gait cycles. And you need that to like stabilize the system, right? Because it's underactuated. And with all these linearized dynamics, this is a convex problem. And you can write this down in general as a QP. So you might have something like, for instance, standard stuff we've done a lot of, XU, cost function, the standard stuff, right? So oops, we'd have like our states, we'd have some reference that we're trying to track. Similarly, controls, which here are remember, these are the ground reaction forces. Same stuff. And then we've got the A and B matrices we wrote down before in discrete time, obviously now. And then we'd have also potentially have these friction cone constraints, which I'll write them down, I guess, right now as like the actual cone, which we did before. But so this is tangential normal. The friction cone is usually linearized, so maybe I'll write down here convex problem. So the way I just wrote this is, this would be an SOCP, the friction cone constraints like that. But we typically linearize the friction cone, like we've talked about before, right? Where we essentially replace the 2 norm with a 1 norm, play that slack variable trick to turn that into a pyramid, which is a linear constraint. And then it's a QP. And that's the standard thing. Okay. In this setup, some notes. So it's sort of difficult here to strictly enforce torque limits because the decision variables in the QP are actually these ground reaction forces, right? So those are only sort of like indirectly and in a very nonlinear way, right, through the kinematics related to the actual joint torques. So it can be difficult to strictly enforce those. So that's another source of conservatism, right? Like in practice, because I don't really have the joint torques in here, what I really want to do is kind of like put a strict, like kind of lower bound on stuff. So I'm not ever going to exceed the joint torques. So I can limit performance. Yeah, output is desired. Foot forces. What else? Yeah. Okay. And then there are lots and lots of extensions, tricks, et cetera, to get this to work in practice. I mentioned a handful of these like, as we went through it, but this is the most basic, like kind of original cheetah controller, I would say, roughly what we outlined. Okay, I think one of the other takeaway messages, you can go surprisingly far with like linear models in convex MPC, right? Like this is a problem that at face value, if you kind of like write it down out the gate, looks extremely gnarly, high dimensional, non-convex, non-linear, ugly, right? Lots of, contact mode stuff, non-smooth. And somehow with all these like tricks and assumptions and simplifications, we got it down to a QP with a bunch of stuff around it, right? And this works extraordinarily well, right? Like every quadruped demo you see running around, right? They're basically all doing this. So it's extremely successful. And at the end of the day, it boils down to like convex QPs that you solve fast with a bunch of glue around it, right? So kind of wild. And I think part of what I want to show you as this stuff is just like get in your head, like these are all tools, right? All the stuff we're talking about in this class, like all this convex stuff, all this trad drop stuff, these are all tools to have in your toolbox. Actually applying these tools in a real scenario on a real robot or whatever your scenarios, you still need to really know what you're doing and there's still a lot of room for creativity in here, right? Like think about like what we just went through. Like this is very far from just like some vanilla convex problem, right? Like it took a lot of insight, a lot of trickery to like get this into this form of a QP. So like that's sort of really where the insight and creativity comes into this. And like you should understand the tools, but you got to learn how to like applying them in specific cases can be a lot of tricks and is really an art form. With that, yeah. All the assumptions, approximations, yeah, all this stuff, right? There's a lot that went in here to get it to a QP. And so that's kind of where it's an art, right? With that, I think we're done.